Hello students, in this video we'll define the Fourier transform of a function that decays sufficiently rapidly at infinity and see some example calculations. So for a function f, which decays sufficiently rapidly at infinity, and we'll specify exactly how fast it has to decay at infinity to make this result work. At infinity, at plus or minus infinity, we define f hat to be the integral over r from negative infinity to infinity of the function f of x e to the minus 2 pi I x c dx. Okay, and this is called the Fourier transform. This is the Fourier transform of the function f at the point. See? Now typically what we use the notation, we call x the spatial variable. So I'm going to call this the spatial variable. And we call xc the frequency variable. Okay? Excellent. And now we can see automatically, we know that this expression where this e to the modulus of e to the minus 2 pi I x c is equal to 1. So in order for this integral to be convergent, the function f has to be going to 0 as x goes to positive or negative infinity sufficiently rapidly to make sure the integral converges, right? So convergence is always an issue here. So just note, convergence is always an issue. And so for that particular reason, we're going to usually think about defining the Fourier transform on a space of functions which decays sufficiently rapidly, as I mentioned. And typically the space we're going to use is called the Schwartz class. So the Schwartz class is a class of functions such that it's C infinity. These are C infinity functions whose derivatives decay at infinity as fast as you like, at any rate of growth you want, basically at polynomial rates of growth, right? So in other words, what these are functions such that the supremum over all points x and r of the absolute value of x to the L, and then f, the kth derivative at x, is less than infinity for all L and k equal 0, 1, 2, etc., right? So in other words, the derivatives can go to 0 as fast as you wish, basically. So that's the Schwartz class of functions. And for these sorts of functions, these integrals will definitely converge, okay? So that's the class we'll think about. But even better than that, what I'm going to do is I'm going to do two examples now of examples of functions that are compactly supported, right? So let's consider this example. Here's our first example. Let's consider the function f of x is just a characteristic function of negative 1 to 1, right? And so what is that? That function over here is just going to be equal to 1 if x is between negative 1 and 0 otherwise. Okay, excellent. So let's compute. Now this function clearly decays because it's identically equal to 0 as you go to infinity. So this function is compactly supported. It's compactly supported. And there's no convergence issue, right? So compactly supported functions are great. So how do I compute the Fourier transform of this function? Let's do it. So it's f hat of xc. So f hat of xc is going to be the integral over r, but this function only turns on between negative 1 and 1, right? So it's going to be the integral from negative 1 to 1 of e to the minus 2 pi I x c dxc. All right, so antiderivative, this is going to be e to the minus 2 pi I x c. I'm integrating with respect to, integrating with respect to x, not xc over here, so that should be an x. It's an x, not an xc. And then I divide by what? I divide by negative 2 pi I xc, and then x goes between negative 1 and x goes from 1. So of course, since there's a negative sign down here, I'm going to plug in the bottom limit first. If I plug in the bottom limit first, I'm going to get an e to the 2 pi I xc minus e to the minus 2 pi I xc, all divided by what? Since I plugged in the bottom limit first and get rid of that negative sign, 2 pi I xc. All right, so now of course we can use Euler's identity. So I know that if I look at these terms over here, this term over here minus this term over here, and then the 2 and an I, that gives me sine. So that's going to give me the sine of that variable. So this is going to be exactly equal to just the sine of what? Of 2 pi xc divided by what's left over, just pi xc. Okay, so oftentimes what you'll see with an example like this is if you divide this function f by 2, then what you get is you'll get the sinc of the sinc function at 2 pi x c, right? So sometimes you'll see this is really equal to 1/2 the sinc function at 2 pi x c, where sinc is just sine of x over x, okay? So it's just a sort of a different notation for that. Let's do one more example. Here's our next example. So this, of course, what does this function look like? This function over here just looks like this. Here's -1 and here's 1. And the function looks like this. That's 0 everywhere else, like that. So it just steps down. So it's a unit step, okay? The next function we'll look at is this function over here. I'm going to consider the function g of x. Here's our next example. G of x is going to be what? It's going to be just 1 minus the absolute value of x for x between -1 and 1 and 0 else. Okay, so now if I want to get the Fourier transform of this function g, what do I do? So g hat of xc is going to be the integral from -1 to 1, because that's where it's supported, of 1 minus the absolute value of x. And then I have this e to the 2 pi I x xc with a negative sign. So notice I can use Euler's formula over here. So if I use Euler's formula, this is going to become what? This is going to become the cosine of 2 pi x xc, because the cosine doesn't care about the negative, cosine of 2 pi x xc. And then I have a negative I, so it's going to be a minus I sine of 2 pi x xc. And then this is a dx over here. So that might look like a crazy integral over here, but here's the important observation. This function over here is a triangular tent, right? So this triangular tent looks like this. There's 1 and there's -1, it's triangular tent, and then 0 else, so it flattens out like that. This is going to correspond to our fair mean. So later on, we're going to see that if I scale this function appropriately, I can turn this function to the fair means. I can turn this function into the ordinary partial Fourier transform, basically, right? Okay, great. Now it's an even function. The cosine is also an even function, and the sine is an odd function. So an even function times an odd function is an odd function. So the odd function integrates to 0 over a symmetric interval. And now I have an even function times an even function. That's an even function. I can just symmetrize this and basically integrate from 0 to 1 with a factor of 2. So this is going to be 2, the integral from 0 to 1 of 1 minus x, and then cosine of 2 pi x xc. Okay, dx. And now we're going to integrate this by parts. This is going to be my u over here, and that's going to be my dv. Okay, and so we're going to get u times v. And now what's the important thing to observe over here? When we do u times v, it's going to be equal to u times v minus the integral from 0 to 1, and there's going to be a 2 in front of everything, of v du, right? Now let's think about what happens when I plug in the boundary limits over here between 0 and 1, okay? So when I plug in the 1 to the 1 minus x, I'm going to get a 0, okay? And then over here, what's going to happen? So let's just do it carefully, right? So let's just do this a little bit more carefully. Okay, good. So what's this going to give us? This is going to give us a u, 1 minus x, and then a v, antiderivative cosine is sine, right? So I'm going to have a sine of 2 pi x xc over 2 pi xc from 0 up to 1. And then minus the integral, with a 2, of course, in front of that, 2, the integral from 0 to 1 of a v du, right? So the du is going to be a -1, so it's going to turn to a plus over here, plus over there. And then we're going to have a sine of 2 pi x xc over 2 pi xc dx. Okay? Good? And so now what? And so now what happens when I plug in 1? I get 0. When I plug in x equals 0, I get 0. So those boundary terms are gone over here. And so we just get this integral over here. And so what are we going to get? Antiderivative, so those 2's are going to cancel out, right? I'm going to have a 1 over pi xc. And then what? And then antiderivative sign is negative cosine. So I'm going to have a negative cosine of pi xc times 2 times xc times x over 2 pi xc. From 0 to 1. And now what's going to happen over here is that we can use we're going to be able to use the double angle for the power reduction formula over here, and we're going to see that this is exactly equal to just the sine squared of pi xc over pi xc quantity squared if we use the power reduction formula over here. So this is the Fourier transform of this 10 function, and that exactly looks like what we saw for the fair kernel when we looked at the fair kernel for the Fourier transform over the integers over here. So here are two examples of computing Fourier transforms, and so it's in particular if you have a polynomial function, or just a very simple function, a polynomial function that's compactly supported that you sort of truncate, you can always compute the Fourier transform because there's no issue of the convergence at infinity. Thank you very much.